Okay, let's take the following example. The enthalpy of combustion of 1 mole of methane is minus 890 kilojoules. Well, what that means in practice is when 1 mole of methane burns, 890, almost 900,000 joules is released. And we can symbolize that as follows. Here's our reaction. Remember, the combustion of a hydrocarbon produces carbon dioxide and water. This is a balanced chemical reaction representing the reaction of 1 mole of methane. Notice it takes 2 moles of oxygen, and you get a mole of CO2 and 2 moles of water. With this additional information, we can also write that delta H for the reaction is minus 890 kilojoules. And again, what that means is if you add up all the enthalpy contained in a mole of carbon dioxide and 2 moles of liquid water at 25 degrees, which is where this is taking place, if you add up all of that enthalpy and then subtract from it the enthalpy contained in a mole of methane and 2 moles of oxygen gas, the difference will be negative, meaning there's more enthalpy in the reactants than the products. And so if you're subtracting a bigger number from a smaller number, you get a negative number. In other words, there's 890 kilojoules less enthalpy required to string together the carbon, hydrogen, and oxygen atoms of CO2 and water compared to stringing those same atoms together as methane and oxygen. All right. Well, if that's true, what would happen if we had 2 moles of methane burning? To do a problem like this, we start with the information contained in the problem, which is that we have 2 moles of CH4. But now we need to convert between the moles of reactant, or product, and the amount of heat that will produce. So, here is the key idea. You always match up the enthalpy or heat. Remember, delta H is measured as the heat that flows. So we take that heat, but we have to match it up with the amount of material that produced it. And if you read this statement, it's 1 mole of methane that produces 890 kilojoules of heat. So we're going to have minus 890 kilojoules per 1 mole of CH4. And you see what I've just done is to turn the information into an intensive quantity that allows me to convert between the amount of substance and the energy it produces in the form of heat. So I took the enthalpy change and matched it up to the amount of methane that produced it. When I do that arithmetic, it turns out that 2 moles of methane burned will produce twice as much energy, or minus 1780 kilojoules. The more I burn, the more I get. But the delta H associated with a chemical reaction is the enthalpy change associated with having this reaction occur once. In other words, it's the enthalpy change when a mole of methane burns. It's the enthalpy change when 2 moles of oxygen react. It's the enthalpy change when a mole of CO2 is formed. And it's the enthalpy change when 2 moles of water are formed. That ability to turn this information into an intensive quantity that allows you to convert between energy and amount is vital to this section. Okay, well, we can take this a step further now that we have that conversion. We want to determine the enthalpy change when 1.5 grams of methane is burned in excess oxygen. Now, in this case, we have 1.5 grams. Okay, our conversion that we just learned about is minus 890 kilojoules over 1 mole of CH4. But of course, this is grams of CH4. So to convert to moles, what I'm going to do is multiply by 1 mole over 16.0 grams. 16 grams, 12 plus 4. That's where the 16 grams per mole came from. So I'm going to change the information from grams of methane
into moles of methane by dividing by the molecular weight. And now I can multiply that by the conversion between heat or enthalpy change and amount. And when I do that arithmetic, it turns out that the enthalpy change for 1.5 grams is minus 83.4 kilojoules. So the amount you burn determines the amount of heat you get, where the conversion comes directly from the chemical reaction. All right, we can ask another question. What mass of oxygen is consumed if this reaction releases 150 kilojoules? So now we're given an amount of energy that we have produced or want to produce, and we're asked to determine the mass of oxygen that it'll take to do that. So again, we're going to start with what we know, minus 150 kilojoules, minus because it's released. So the system's energy must go down by 150 kilojoules. Now, what's the relationship between the energy produced and the amount of oxygen that's consumed? Well, you can see, I think, that that relationship is minus 890 kilojoules per 2 moles of oxygen, because 2 moles of oxygen are consumed when 890 kilojoules are released. So I can write that in to convert between energy and amount, but I'm going to put the energy on the bottom, so kilojoules will cancel, and I'm going to put 2 moles of O2 on the top. So this is now telling me how many moles of oxygen will be consumed when 150 kilojoules are released. However, the question was what mass of oxygen, so the last step is to multiply by oxygen's molecular weight, 32 grams per mole. Now, it follows that if we were to do the reaction in the opposite direction, instead of burning methane and oxygen, we took carbon dioxide and water and remade the methane and the oxygen, we'd have to put that energy in the form of enthalpy back in. If we release it when we burn methane, we're going to have to put it back in order to form the products. It takes more energy, 890 kilojoules more, to hold those carbon, hydrogen, and oxygen atoms in the form of methane and oxygen than it does to hold those same atoms in the form of carbon dioxide and water, which is why burning methane produces so much energy. Now, that's not to say that I could put CO2 and water in a bucket and pump in 890 kilojoules and expect to make methane and oxygen. The world is more complicated than that. I mean, I wish we could do that. We would solve the energy crisis pretty quickly, but we can't. So, the point here then is that depending on the direction you go, the amount of heat released or absorbed is the same. It's just a question of it being released when you burn methane and absorbed when you make CO2 and water back into methane and oxygen. So, let's go the other way. Let's take 0.6 of a gram of carbon and burn it in oxygen. If we do that and measure the heat that's released, if we do that, 19.7 kilojoules of heat are released. We want to know what the heat of combustion of carbon is. All right, well, we're burning carbon, and when you burn a carbon or a hydrocarbon, your product is going to be carbon dioxide, and in the case of a hydrocarbon, you're also going to have water. So we want to know the enthalpy change for that reaction. There is no delta H here anymore. In fact, delta H equals a question mark. But we do know something about the energy. We know 19.7 kilojoules of heat are released when 0.6 of a gram of carbon burn. So we can write minus 19.7 kilojoules, but again, you always match up the heat with what produced it. In this case, 0.60 grams of carbon. So you need the relationship between the heat that's produced or absorbed and the amount of material that produced it. In an example like this, you're told the amount of material, as opposed to the previous example where you were given the delta H for a reaction and you got the amount of material based on the balanced reaction. Well, we want this per mole of carbon burned, so it's minus 19.7 kilojoules per 6/10 of a gram. If we want to change that to moles, it's going to be 12 grams, 12.0 grams per mole of carbon. And if you do that math, it turns out minus 394 kilojoules is the amount of heat released when a mole of carbon burns. So I got the information from the problem because it told me how much carbon produced how much heat. All right. Now we look at the enthalpy change in the reverse direction. So we know the delta H for the forward reaction is minus 394 kilojoules. But what about the reaction shown below it? Well, there are clearly two different things that happen to the second reaction compared to the first. And the question is, what's going to be the effect on the enthalpy if the first equation becomes the second? Okay, we got minus 394 kilojoules in the forward direction, making a mole of carbon dioxide. But this time instead, we're reacting 2 moles of carbon dioxide. So the second equation is both turned around and doubled. We turn it around, that means we change the sign, minus, and we double it means we double also the enthalpy. So minus 394 times minus 2 makes the enthalpy change for the second reaction plus 778 kilojoules.